Hello everyone, thanks so much for coming this afternoon. My name is Boyd Goodson. If you don't know me, I'm Associate Dean for Research, but I'm also a Professor of Chemistry, and that connection will be made clear in a second. I teach Honors General Chemistry here, and many years ago, I once had a student named Drake Anthony. And before that, I had watched videos on YouTube from time to time, and I see some kid who would be blowing stuff up or using some laser, doing something crazy named Styropyro. And you can imagine my surprise when one day I made the connection with Drake, this kid in my class, is Styropyro, right? So already had a kid in my class who was more famous than me. The freshman too. So I thought, oh, I've got to get this kid recruited into my lab. I think Lee Chang helped make the connection, and Drake joined my lab doing fun laser stuff in the lab. Basically, I let him do whatever he wanted as long as he also did the things I wanted.
Yes.
That's right, it's a lot of fun. And unfortunately, all things come to an end. Drake did graduate, unfortunately for me, fortunately for him. And I followed his progression through the year. He is basically a professional YouTuber. He has almost 3 million subscribers. His videos have been watched, I would say, upwards of hundreds of millions of times. You can watch a bunch of them there. I have my favorites. I think of the first handheld high-power laser, the laser bazooka.
You gave me the name for that. Oh, the laser bazooka. That was your naming, yes.
Oh my goodness.
Yeah.
I'll take the profit.
Yeah.
The laser turret. I really like some of the chemistry things he's also done. The exotic thermites video.
Yes.
There's also a really neat video that was shot in my lab that you can watch where I learned something, and I won't spoil it, but it's what happens if you take a laser diode and you put it in liquid nitrogen. Something interesting happens. My least favorite video, I think, has got to be their storm chasing ones.
Oh,
as a parent, I watch these videos. They are so terrifying. I think to myself when I watch them, you control these lasers, Drake, but you don't control that tornado.
That was some of the safest stuff that I do. Yeah.
Okay, well, we're going to learn a little bit about some new dangerous thing that Drake has been up to. I'm really excited to hear about it, so won't you please join me in welcoming Drake back to
I forgot to see if I have audio with this. Is there a separate audio cable, or will HDMI do that too?
You should.
Okay, then I'll just get going. Okay, yeah, so let's get started.
An audio maybe?
Yeah, I guess I'll get to that point, and if I have an issue, then we'll get there. So yeah, so a little about me. Dr. Goodson just explained some of my background. So I actually graduated from SIU in 2016. So it's crazy, for me. It's been that long since I've been here, and it's even weirder for me to be in front of the lecture podium. So that's a pretty weird feeling for me. Then yeah, I've ran my channel on YouTube since 2006. So it's been almost 20 years. And then, so on my YouTube channel, I talk about mostly like mad science things, lasers, chemistry, electricity. But I like to spice it up with, some other stuff like moths, tornadoes, and squirrels. So, just to keep things diverse. So, today's talk is about 400 car batteries. That's like my current project. But a couple years ago, I did this project with 100 car batteries. So I figured that it'd be beneficial for me to explain some of the issues I had with that project. So this started out in a really bizarre way. So a company reached out to me, completely unrelated to car batteries. They just wanted to see what would happen if I wired 100 car batteries in parallel. And this is just like, there's so much to unravel with this, just because it's such a ridiculous thing to ask, but it's also really genius because at the time, well, I should back up. If they want to see them all in parallel, they probably want to see a lot of current. And I had already planned on doing a video about high current. I was just going to make a big transformer for it. But in hindsight, it would have held a candle to 100 car batteries. And sure enough, the deal actually happens. They actually buy me 100 car batteries. I was skeptical, but they did it. So my goal for this one was to achieve the currents that you see in a lightning strike. And then here I have a nice still frame from a video clip of a lightning strike that was pretty close to me. I think it was like 90 meters from me. So it was my ears got rocked on that one. But a typical lightning strike has a peak current of 30,000 amps. So I at least wanted to hit that. So this brought up the issue of how do you switch that? So, you know, this is it's such a bizarre electrical regime because it's like insane amounts of current, you know, tens of thousands of amps. It's not just a brief pulse, it's like, you know, maybe a full second. And then additionally, it's like low voltage, so it kind of rules out all your like gas discharge devices. So this was like a really big problem to solve. I was thinking, man, I maybe should have just done the transformer instead because switching AC is so much easier. So I looked at industrial contactors, which are like, you know, big relays, but nothing was even close to the ratings I needed. I looked into some solid state stuff, but again, it's like, I knew it was theoretically possible, but when solid state components fail, they fail short. So it's, you know, those failures would be dramatic. I asked people online, and I think my favorite suggestion was to take 2 big copper blocks and just dump like a bucket of mercury through them to switch it on. That would have probably just made a bunch of mercury vapor, which would have been so delicious. And then, you know, explosive bolts were brought up, but what I ended up doing was a combination of the last 3. So what I did was I bought a lot splitter from a local farm store, and this one is electrically driven, but it's still hydraulically actuated. And at the time I couldn't weld, so I brought it to my friend with these like big copper blocks and had him weld together some switch plates. So the idea is there's an internal spring that slams the copper blocks together to turn it on, and then the hydraulic part, the log splitter part, rips the plates back apart. And the reason I had it arranged that way is because the plates tend to weld at, you know, tens of thousands of amps, so you need a lot of force to yank them apart. And then the switch just, for the rest of that 100 car battery project, the switch, it just worked perfectly, which in hindsight is amazing to me that it actually happened that way, because this was such a big challenge. But yeah, it just worked. So that was, in the video I barely talk about it because it just works really well. So the issues I did face was, you know, I wired them all in parallel. That's only like, you know, 12.6 volts. But I can only get 15,000 amps this way. And this was kind of surprising to me, you know. And yeah, I guess only seems relative, but it's only 150 amps per battery, which car batteries are capable of far more than that. So, you know, because I was looking at like the main, let me go for it. I was wondering, why is the current so low? So, you know, the circuit is like, it's like the first circuit you'd see in an introductory electronics course. Is like, how hard can this be? It's, you know, a battery, switch, and resistor. But of course, it's really more complicated than that. There's all these, you know, all these resistances adding up. You know, and a lot of these are dynamic. They're not like, they don't follow Ohm's law. But you know, to be quick, it was the contact resistance that was the big number. So just, you know, where you take 2 pieces of copper and stick them on top of each other, there's like a little oxide layer. That was the big contributor. So to overcome that, I rewired the bank for higher voltage. So it's so now it was strings of 5 batteries in series, the rest parallel, 65 volts. So that way there's more, that voltage can overcome the resistance. And so it increased my current to 45,000 amps, but it did bring up new issues. Although interestingly, the contact resistance dropped. So it was so that was kind of a weird thing. It didn't follow Ohm's law. I think that has something to do with the semiconductor properties of copper oxides, or at least copper 1 oxide. So I did run into some magnetic issues. Hopefully the audio plays on this. Okay, yeah, so basically I'm trying to zap a bolt here. And the problem is, it was really hard to hold bolts onto these blocks. So I couldn't, so you can see it didn't actually melt through. So it's like, what's going on here? Heck. So here's a slow-mo, and you can see those copper blocks are getting yanked apart. And this is a magnetic effect. And then, so if you look at the cables, you can see how they're all attracted to each other. This is another magnetic effect.
Whoa, that's great.
Yeah, it takes, and then there's 2 effects that happen here. So, and I'm going to play this one again. So the cables holding current in the same direction all get squeezed together, and then also the loop expands, and that loop expanding is what was ripping apart the blocks. And again, yes, magnetic issue. So this is a consequence of the Lorentz force, at least the magnetic portion of it, which is the force of electromagnetism. And in the special case of the magnetic force between wires, you have currents going in the same direction attract each other, and in the reverse direction they repel each other. And if these are all currents in the same circuit, whether it's like one current on two sides of the same loop, or like parallel strands of currents carrying like equivalent fractions of the same current, then this I1 equals I2, and you get this I squared term. So basically, these magnetic forces scale with the square of current. And this is a theme for a lot of what I face in this project, is a lot of force and then also resistive heating scale with the square of current. So that number starts getting really, really big when the current goes up. So then I guess one other magnetic issue I had was I couldn't, even after, so I bolted everything to this wooden block. But it made this oscillator, so there's this additional magnetic force that wanted to launch it off it wanted to launch the object off of the blocks. I've never really solved this one, but yeah, I made this funny oscillator. And then I also wanted to crush a pipe magnetically with these 100 car batteries. I'm just going to play this part of the video because it'll save me time. So this is like the ending of this first video.
My most disappointing failure was trying to crush a pipe via magnetic pinch. So back in the late 1800s, a lightning rod was mysteriously crushed inward by a lightning strike. And then in 1905, a couple scientists made the connection that it was crushed magnetically by the huge currents that passed through it. They estimated that a current of 20,000 amps, along with some melting, is what did the pipe in. In order to replicate the effect, I rigged up some pipe with fuses to prevent the pipe from melting all the way through. With each trial, I made the fuse thicker and thicker, which allowed the pipe to heat more and more with each run. I was achieving currents of over 40,000 amps, and the fuses were detonating in these trials. Unfortunately, there was no pipe crushing, even when I let the pipe itself pop from the current. It turns out, it was the alternate explanation that was closer to being correct. A later analysis determined that the rod was actually hit by an unusually powerful superbolt of 150,000 amps, with no melting at all. Since the pressure in the pipe is proportional to the square of the current going through it, that means I'm not even getting close to what's needed at 40 kiloamps. Now if I had a few hundred more car batteries, well then yeah, I could pull it off. But for what that would cost, I'd rather build a more accurate lightning machine.
So, oh yeah, well, it's funny where this went, because it's that same company that bought me the 100, they're like, oh actually, let's just buy the 300 more car batteries. It's like I can't turn something like this down. I know it's going to be just a nightmare of a project, but it's like this is just so ridiculous. I'm going to do it. And sure enough, they give me the money. And it took like 3 truck deliveries to get those batteries out of there, but these batteries show up, and the goal with this one was to achieve like lightning superbolt current, the top 1% of lightning strikes, which kind of depends where you are in the world and also how it's measured, but a top 1% strike is about 100,000 amps. But the other thing is lightning is only for like, those currents are only for like 10 microseconds, at least at that magnitude. So, and I can do it for like a second. So that you're talking like almost 1 million times longer there. So it's like this also it's like a rare opportunity to see some of these like electrical effects that have never been filmed before, because like you could go to like an aluminum refinery and see what 100,000 amps looks like on a giant like thing of bauxite or whatever. But in terms of like putting this thing for like pipes and bolts, that footage doesn't exist. So this is a cool opportunity. So I wired this together, and this is like 2 months of solid work here, because I leveled the ground with a shovel and had to make all these custom crimped cables. So there's like, oh gosh, I can't remember, like 1,000 custom cables. And the worst part was cleaning every contact point right before joining them, because I need to make sure there's no oxides and I get the most current. Including sanding 800 lead contacts. So delicious metallic lead sanding is always a good time. And then the other thing I should point out is, in hindsight, I realized that with the first set of batteries, I would have got more current if I had 3 or 4 in series as opposed to 5. But I realized that with 400 batteries, this is probably a better impedance match. So it's like I had to just take some data to, just short-circuiting an ungodly amount of car batteries to know how to better optimize this bank. And I also have the ability to wire for higher voltage in the future because it's separated into 8. So then this brings up the issue of how do you switch 400 car batteries? So I figured that, the log splitter idea worked for the first one. I figured I'm going to use the same idea, but just use bigger copper blocks to handle the more current. So I figured I was going to get 3 times more current, so the copper blocks will be beaten up 9 times more. So I need, approximately 9 times more copper. So I bought 300 pounds of copper bars, and this was machining copper is a living nightmare. It's horrible to machine copper. But then I realized something really bad. So what did I do with my oven? So this is, I already ordered the copper, had a design in mind, and then I realized I was looking at the old switch. I knew this was an issue, but you can see that the switch really only wore down on one side, so it was like it was misaligned. But I wasn't too worried about it because it actually didn't matter for the 100 car batteries. Because yeah, it would hit an offset, it would hit in like a really small area at first, which would just explode off, and then expose more, and then you'd have this like liquid metal contact point. So it was all continuous metal conduction, and the resistance was extremely low. So it worked well, but I just figured it was slightly misaligned, even though I never noticed it when I would dry fire the switch with no load. But then it hit me. The way I was feeding the cables into this, it was all chaotic. But basically, there were more currents entering this side and leaving this side compared to this side. So that forced the plates open on that side. So it was a magnetic issue. Then I realized that, if this thing was barely being closed, if I get triple the currents, my forces are going to be 9 times higher on these switch plates. So this could be a big issue. But I just decided to, I'm just going to try it, and if it's an issue, I'll deal with it. If not, then I'll just, then that's great. So I learned to weld for this one, and weld together an abomination. And here's what the finished switch looked like. So I have, there's like more than 1,000 pounds of copper on this whole thing. It's just incredible amounts of copper, and like, man, everything was heavy. I had to set 28,000 pounds of car batteries, in this whole setup. And I did that all by hand, and just all the steel and copper. It was very, wore me down. And I also used this boat winch to load up the spring because it's, I really yank it back, and it's a big spring. Oh, so the big change I made from the start was instead of having 1 loop of current, I have 2 of these opposing loops here. So the idea was that the magnetic fields would cancel in the center, so nothing would get launched off to the side. It would cancel out some of those forces, and it also decreases the circuit inductance that way, which matters for a few experiments. So I start off with some small tests because I figure I don't want to throw like the big things at it and have it catastrophically fail at like 10 megawatts. So I start with just this like 3/8 inch galvanized steel rod. So it's not that impressive. It burns through pretty quickly, but it's, the small diameter limits the current. So there's a still from that. It was pretty explosive, but I also filmed this with my new slow-mo camera, so it shows some cool effects here. So the big kicker before you watch this is that the boiling point of zinc is lower than the melting point of iron. So you can see it had some trouble getting started just because it's trying to get magnetically ejected off the blocks. But there's the zinc boiling off, reacting with air. And there goes the iron. Yeah. Isn't that crazy? Yeah, so that's shot at nearly 4,000 frames per second.
Did you make X-rays again?
I doubt I made X-rays, just because it wouldn't be hot enough thermally to make X-rays, and there's no vacuum to get electrons going really fast. Although maybe I shouldn't be so confident in that. Maybe I should put detectors out there. What's that?
Fluorescence.
Oh, look for X-ray fluorescence. I guess I do have an X-ray detector that's good to pretty low X-ray energies. It's 10 keV. I could stick that out there, and because I worry about that with my vacuum devices, but in air, I doubt that's an issue. So at this point, I start putting bigger loads on to see what happens, just working my way up. So this is a 3/4 inch bolt. So you can hear it sounds like it's oscillating. And sure enough, it is oscillating. So, this is not an AC source. It's a bunch of car batteries. So, there's clearly some oscillator being formed there, and it's limiting the current. Because this is a peak of like 55 kiloamps, which is, pretty lame. But again, the steel was probably limiting the current here too. So I start looking for the source of these oscillations. So I start, putting my. So I should take that back. So I realize that the oscillations are either coming from this block, or they're coming from the switch, or they're coming from both. So I point my slow-mo camera at both of these, and I don't even remember what's in this video clip, but I know it looks like I have a steel rod on the bank, on the block. So you can hear it oscillating. And you can see it's, there's some, oscillations there, and it was probably hard to tell, but it pulled a washer and glued it to it from the magnetic forces. Well, that was just a block of aluminum. And you can see that jumping of those clamps there. I think that was like 40,000 amps in that shot. What was that? Oh yes. So this was a copper cable, and this one, the blocks were an issue because you can see it like yanks the clamps off, and I'm not even confident on exactly where this force is from. But yeah, so I clearly see that these blocks are an issue.
Kind of looks like the wire itself is trying to curl in.
Yeah, but like there's still external forces on it. And I guess the other thing I should point out is I also pointed my slow-mo camera at the switch, and I never saw it bounce. So now I think, okay, well maybe I just need to put more current through the system, and I can start seeing it'll be more conclusive. So I use this quadruple-aught copper cable as the load. So I want to talk a little bit about this cable here. So I have an example. So this is like one of my custom crimped cables. So it's really thick. It's really thick cable. And quadruple-aught is the biggest standard wires, size in the American wire gauge system. So it's real thick. I use 40 of them to feed the load on my bank. But this American wire gauge system is pretty ridiculous. Like if you go to the Wikipedia article, there's all these like just horrible formulas. It's just so ridiculous. It's from 1857, and it's like the most American measurement system of all time. And specifically, if you go to the rules of thumb section in the Wikipedia article, look how it starts out. The 6th power of the 39th root of 92 is very close to 2. How is that even? That's just like the most ridiculous statement of all time. But yeah, and that is why American wire gauge is the most American measurement system. But ridiculous. So I start throwing some of this, cable in there. So in this one, everything bounces. I thought the switch was fine, so I put in my slow-mo camera at this, but then I could see that the switch had some issues there. And I think I zoom in on that. So basically, I could see that the switch bounced there, so that was important. But this also brings up another annoying issue that I face is sometimes when I put something on the blocks there, it melts just barely off the blocks, and because the voltage is so low, it can't strike an arc and keep it going. So that means there's it might be less than a millimeter between the load and those copper blocks, so it's just waiting to explode again. So then I have to safely clear that. In there. So I usually just use a machete for that. And you can see how it's just sparking like that. So I have to safely clear it. Where's my science machine? Oh shit. Not enough? there's a lot of things I miss about working in an academic lab. I doubt Dr. Goodson has the science machete in his lab.
Maybe you need like a wooden training sword for it, right?
Yeah, but I like the machete. So now I got a peak of 76,000 amps, and it's clearly this like chaotic oscillation. So there's clearly an issue. So I decided to like kind of sidestep the issue with the blocks. I know the blocks are an issue, but at least for the sake of cable, I decided to start C-clamping the cable. So most things you can't get a C-clamp to work because the contact points are going to heat more than the rest of the bulk material just from like the oxides. And if it's a rigid object, that means those contact points are going to shrink, and then it's just going to get magnetically ejected. But for cable, you can spread it out and sidestep that issue. So I wanted to see what was wrong with the switch. I start with some smaller cables just to work my way up. So that looked like a fast, clean pulse. And one thing I want to point out is look how fast these sparks move above it. They're really calling, right? So my slow motion camera is pointing at the cable for this one. So it doesn't bounce much on the blocks because it's C-clamped, but you see it fly back. And I did an estimation based off the distance between the blocks, and I think that cable is moving at 190 miles an hour. So it was really, or I guess like 90 meters per second or something. So yeah, that was actually 2 pulses. So it sounded like one big explosion, but no, that was actually 2 pulses. The switch bounced on that one. And another interesting note is I've noticed that the sound of the explosion depends only on the current right as the object breaks, because I think it's inductive kickback causing that like sound. So now I clamp some of that big copper cable on the blocks. So you can see like there's a lot of things going on here. First, I want you to notice there's like some bolts and stuff under there that get slammed against there magnetically. And the switch, of course, just gets like really beat up, bouncing back and forth. So yeah, switch is an issue. Yeah, so I pointed in slow-mo at the switch, and look, watch this. It burps up a plasma toroid, which is incredible, but I can see that the switch plates are getting blown apart there. So on this one I measured a peak of 89,000 amps, which is, not where I wanted to be. And it's, again, this horrible chain of pulses. So, I realized I need something to close the switch better. So I figure I can either, let me put this down. I figure I can either, fight the magnetic forces with like huge springs or something, because eventually with enough force I'm going to beat the magnetic forces, or I can use the magnetic field in my favor. So I figure if I rewire the switch, because the magnetic forces in the switch are coming from this like half loop of current that opposes on both sides. So I figure that if I switch it to a configuration like this, then there's on both sides of the plate, assuming it conducts through the face of both plates, there's going to be a component of current going this way in both plates, which means there's a component of force that's attractive on both plates, which would also be additionally helped by these opposing currents here that would also squeeze the plates. So I figured this is probably a good idea. So it takes me like several days to rebuild the switch just because everything has to be cleaned and polished. Every minor change to this thing is very tedious. But yes, I build that Z configuration. But it doesn't fix all the issues. So it oscillates faster, but it didn't fix everything. Only measured 90 kiloamps there. So I also started encountering another issue where my C-clamps weren't enough to hold things in the blocks. And so in that case, it ripped the block off, and the cable was just going slap, slap, slap against the cables there. And this happened another time here too. I'm just slapping, it's so funny. There I got a pretty clean burn through. But it still bounced. So again, there I measured 94,000, which, I wanted at least 100 before I start, even post anything. And it squeezed, the new configuration made the pulses faster, but it was still closer together. But then I realized I encountered a new magnetic issue. Shoot. Oh yeah. So the Z switch is a Z pitch. So it started forming this like small crater in the center of both plates. And you can see how there's like copper splashing out from this, radially from that hole there. And I did not drill that hole there. What's happening is like a plasma is being formed as the plates strike, and then the huge magnetic field from just its own current squeezes it into like a really fine filament. And as it gets, I presume, as it gets crushed between the plates, it just goes off like a bomb. So that's just like, I've done a lot of crazy, experiments in my life. I've never encountered an issue like this, because it's just such a ridiculous issue to have to face. So I figured maybe I need a way to vent these plasma gases. So I start by adding copper to the switch, because I know it's going to just weld on. This wasn't enough copper, but I just wanted to see what would happen. See what would happen if I just put that in between the plates. No, it didn't work at all. So this one's important though. So now I put four of those quadruple aught cables just side by side, again hoping that the gases can escape. And it's funny because like it's just barely connecting, but of course it's just going to weld the plates and it's going to conduct after that. Very much louder. Sorry for the speaker. I should turn this down. But either way, it's far louder. And also, you can see that these cables jump like crazy on the shot. So let me, if I can maybe turn down the volume a little bit. Okay, because a lot more explosions coming up. So I noticed this was bolted to this wooden block here, and it ripped like the nuts through the wood block there. It ejected one of the C-clamps, and then so I brought this here. This cable was like, because it's a bunch of smaller cables in a bundle, and as it melted there, it actually I noticed it squeezed it, so it like crushed the center piece here. So I see it got magnetically crushed there in the center. So it looks as if it looks as if I've increased my current here. But I only measured, 94 milliamps. So it's like, well, that's disappointing. But then I realized something. So, this is about the total pulse is like 100 milliseconds. And really, you can ignore about the first, I think, 30 milliseconds or so, because it only gets to 20,000 amps in that time frame, which is essentially negligible heating compared to the rest of the pulse. So then, the rest of this pulse, this cable melts in 70 milliseconds. So there's this old equation. I don't even think they know who this guy was, but it's referenced a lot. And it turns out it's really accurate for short time scales. It gives a measure of how fast metal of a known diameter will melt at a given current. And it does not take into account heat losses in the environment. And it does take into account the change in resistance as the metal heats, and it does not take into account like the heat of melting of the phase change. So it estimates on the low side. But before this project, for the 100 car battery video, I made this whole Excel spreadsheet because I have to, for safety reasons, I have to fuse my bank. And so I realized that for this quadruple aught cable. At 150,000 amps, it should take 70 milliseconds to melt a cable. So it looks like that was actually a 150 kiloamp pulse. So I realized that maybe it's my sensor. So my sensor is actually just a Hall effect DC current sensor, and it was just the biggest one that I could buy that had a price was 20,000 amps. So I stuck it on one of the 8 sub banks, and then extrapolate based on that. It's not perfect, but for what I'm doing, it should be fine. But clearly, there's a good chance that this was saturating. So I moved, instead of having 5 cables go through it, I moved it to just 1. So if the sensor wasn't the issue, then this will just cut the value I see, it'll be 5 times lower. But if the sensor was saturating, then I should start getting bigger numbers. And sure enough, I get bigger numbers. So I couldn't get those clean pulses anymore, as hard as I tried with those cables. But I still, just that night I got a peak of 138,000 amps. So I decided maybe I need to add different forms of copper to the plate. So I start by taking the small plate from the first switch, and I wanted to see if that might, it was kind of kicked off at an angle, so I was vent off some plasma gases, but it didn't work in that configuration. And it still made that crater in the very center, even though that wasn't like the closest point. There I got a clean burn through, but still. Okay, so this time I figured maybe I just need to allow this to reach a steady state. So I put 2 of these cables on the blocks there, so that actually quadruples the energy of the shot. If you split the current in half through a cable, then the heating is now 1/4 of what it is. So that means it takes 4 times as long to melt. So I was hoping that eventually that other plate would weld onto the switch, and well, didn't work out. So just made this like ridiculous oscillator, which interestingly, it's so regular and periodic. Like I'm kind of shocked how nice that looks. But peak of 140,000 amps, so that's like 9 megawatts. So yeah, it's clearly that didn't work as well as I had hoped. But it was so cool and violent that I decided, well, how about I just stick some metal inside the switch itself to see what happens? So this is steel. Some nice sparks. Can't remember what this next one is. Probably aluminum. Just a nice hot plasma. It was supposed to be zinc, but the zinc fell out, and used the copper. So then I think this next one, yeah, so I popped my fuses on this one, and then I realized that the magnetic forces had untorqued 2 of them, so there was like some oxide and it was limiting the current. So when I replaced them, then I measured a peak of 176,000. So yeah, like some of these shots, like liquid copper makes it above the treetop level. So it's oh, and then this one, I forgot about this. So this one, I put aluminum in the switch just because aluminum is really, it illuminates well because it burns in air at really hot temperatures. I put a bunch of like bolts here, and look what happens to them. So they all start like magnetically levitating and thrown towards those cables just from being magnetically attracted to them. So. And like I lose so many tools this way, so I have like wrenches and stuff nearby, and then they all just it's like a black hole, and all my tools disappear because they're all get magnetically thrown around, and sometimes it throws things onto the batteries. So it's like the magnetic forces get pretty ridiculous. How much time do I have? Let's see. Okay. So I decided that even though the switch sucks, I still get big peak current. So maybe I can still crush a pipe, because that's really what I wanted to do. But the issue is the circuit has a slow rise time, 15 kiloamps per millisecond, just because it's like there's a relatively high amount of inductance for the voltage. And the reason why that matters is then, if it's too slow, then the pipe will melt before there's enough current going through it to magnetically crush it. And then there's also this also implies another thing. So it implies that the circuit inductance is 4 microhenries, which doesn't seem like a lot. When you put 175,000 amps through that, that's like 60 kilojoules of energy in just the magnetic field around it that's ready to kick back and raise the voltage. So even though the starting voltage is low, that's capable of probably some lethal pulses just from the inductance alone. So I start by zapping pipes. And I use, so my idea is I use a fuse because I want the fuse to explode before the pipe does. So yeah, I use a smaller amount of copper in the fuse. And I also use this parallel parallel fuse to shunt away just a little bit of the current from the start, just because I know I just need to shave off as much of that initial current as possible. So I use these parallel fuses to start. And so that one doesn't crush the pipe, it also doesn't make that much current. So let's see, so I use bigger fuses, try it again. So then I use even bigger fuses, but it like EMP'd my camera, so I missed it with the other ones. Yeah, so like all my cameras have had these crazy issues, and I realized it's probably from like the magnetostatic fields, which is crazy because like I think my worst like electric burn that I've ever received was I was holding my camera near a Tesla coil, and then my camera just like arced over to my hand and burnt my hand really badly. But like my camera is fine in like electric fields, but it seems that these magnetic fields are causing these crazy issues with my cameras. But on this one, my slow-mo caught it. So you can see what happens. So it bent a little bit there. I don't know how much of that was just like the upward force crushing it versus the actual pinch. But then at this point, if I use a bigger fuse, then the pipe is going to melt before the fuse. So I decided I'm just going to try blowing up a pipe and see if it crushes as it melts. Because I couldn't do that with 100 car batteries. And notice it actually just like disappeared. So, so then I spent some time looking around the yard trying to find this thing. And I was all like freaking out. And here's a slow-mo from it. So yeah, it got magnetically launched, but you can see it does get crushed. And there's the remnants there, so it was a partial success. I cheated by melting it, but it did crush the pipe. So at this point, this is a dumb idea. But, so I was thinking that, well, maybe if there's just a little bit of heat transfer, it'll buy me a little bit extra time. Because I was already achieving 100,000 amps. So I figured like it's probably not far beyond that where I can start crushing the pipe. So I just need a little bit of heat transfer to buy me some extra time. So I was hoping that I could do it this way. And then I also use this 200,000 lumen flashlight to illuminate. It's not full power here, but I needed a super bright light source for the slow motion camera. So you can see me running here to do this.
I like the safety tree.
Yes. Okay. Well, yeah, so the aquarium broke, so here's the slow-mo on that. And the pulse was actually 2 pulses, but, so, it started to crush there. It did start to crush. But then it just exploded. But look, isn't that a cool explosion though?
That's good, right?
Yeah. Bang, yeah, I thought that was pretty neat. And it did pinch the ends of it. It did crush the ends, but still, I want to do it without melting. So, I haven't done these experiments yet, but for future pipe crushing attempts, I'm going to try pre-cooling it in liquid nitrogen because the resistivity of copper, at least in pure copper, is like 10 times lower at L2 temps. So that means there's 10 times less heating from the start, and it might buy me like 10 more milliseconds. That might be all I need. I could try rewiring the bank for a higher voltage to make it faster turn on, but then I have battery resistance to worry about, so maybe I just need more car batteries. Then the other idea is put a giant low melting point fuse in parallel with it, like maybe a chunk of sodium metal. The idea with that is that the resistivity won't change much as it heats, then it'll just melt, and then all the current will get dumped into the pipe. And, then I'd have to blow up a huge block of sodium metal, which would be fun. Yeah, so then I realized it's like, okay, well, I need to fix the switch. I would have liked to use SCRs, because I realized that this is doable with SCRs. It's like a, solid state. It's like a transistor that you can't turn off, but it can handle big current. And I figure I would turn it off by what I'm hitting exploding or the fuse is exploding. So SCRs would work. But I can't find any of the none of the big ones are in stock. And if they were, they're also really pricey, so it's kind of sketchy to use those. So I figured, I should use either more springs or hydraulics. And I go to springs because that seems like the lower hanging fruit, easier. So I get these giant springs, And I mean, they're so big, like, I have a 1,600-pound winch that just barely, pulls them back, and just there's barely any distance, and it won't take it back any further. So they're really, really strong, really strong springs. Didn't do anything. So adding all this additional force did nothing. It didn't change anything about the circuit. Then another thing I realized is that, I realized that on top of, because I didn't really investigate super hard into the formation of this plasma between the plates. I did some additional things, but I was going through my slow-mo and I saw that the plates do get ripped side to side, so there's like a torque on the switch, and I figured that could play some role there. You see all the all the sparks there. So then I decided, well, all right, I'm gonna put rails on the switch to prevent it from going side to side, and I also just used 2 log splitters now. So now I can use the hydraulic to crush the copper plates, and yeah. So and let me say, welding on this whole thing you can't turn batteries off. So I just lay like my welding tank on and hope it doesn't touch the contacts, and because it's like. It's stressful because like everything's live, and I'm not worried about being electrocuted, although it does shock me. It just tingles if my hands get sweaty. But I'm worried about eating a face full of like metal vapor. But so it's I've spent a long time reinforcing the daylights out of these 2 things, because even that last clip I showed you where the plates are bending. I mean, if I rock it with all my force, it just barely moves. So those forces are huge. So. So I have 2 log splitters, because one log splitter crushes it, and the other one will rip it apart when it welds. And I only got to make my first test of this 2 days ago. So I only got the initial ones, and it's better, it's not perfect. So in this waveform, it has a few bounces, but they're pretty close. Then it kind of hits the steady state, but then what happens here is then it rips the C-clamps off the blocks. So now the blocks are going to be an issue. But I at least had this 160 kiloamps for quite some time, at least a few tens of milliseconds, and so at least now I'm going to go back and now I'll probably just do my experiments with this. I really would like to use SERs to switch it, but now I'm running out of time just because it's about to get colder, and car batteries, any battery, the chemical reactions go faster when it's warm, and so if it gets cold, then it limits my current. But yeah, that's where I am. I was hoping I would have this project done before I came here to speak, but nope. I've been fighting those those crazy magnetic effects. But yeah, so that's it.
We have some time for questions. Just raise your hands.
Yeah.
Let's begin.
So what do your neighbors think about this?
Yeah, so it's funny you bring that up. So I moved to I live in the middle of nowhere for the most part. It's like farm and forest surrounding me, and I'm on a decent plot of land that separate. It isolates me, so I don't have people complain. But it's funny. My closest neighbor came over the other day, and she was just giving me some eggs and stuff. And she's like, "Oh, well, I was on in I was with my husband, and we heard you hunting." I'm like, "Hunting?" She's like, "Yeah, well, you're shooting in the woods." I'm like, "Oh no, those were electrical explosions." Yeah, just 400 car batteries in the yard, Yeah, but I don't have many neighbors where I live, Yeah.
Questions, raise your hands.
Yeah.
So how do you plan on recharging all your batteries once you
Well, I constantly recharge them. I started with just a lab power supply, and because if I only do a few experiments a day, it's you just run the charger all day and it gets back. But then for this recent one, I just built a power supply that charges them, and it charges at 1,500 watts, which is still slow, but it's enough, Yeah. Then you had a question.
Yeah, what's the cleanup like after all of these tests?
Oh, so the cleanup, what's the cleanup? Oh, that's funny, because right now my yard is just a complete wreck. There's metal pieces everywhere, there's, even after the first video, I'd find random pieces of bolts and stuff around. It's just, I usually wait until I'm done with the experiments before I even attempt to clean, because I'm going to make more messes, So it does get messy, especially when, things are getting launched really far. Like in one of mine, this is pretty sketchy. I like a molten blob of copper got thrown up onto my workshop roof, and luckily it's metal, you know. I'm just like, oh, you know, I don't want that on my wooden house. So, yeah.
Here,
Where?
any questions? Yes, Jackson.
Not related to the batteries, but to the lasers. Our buddy who's out of town was asking, do you make or purchase your laser drivers? And if so, where do you get them?
So, you know, the laser, I make it, nowadays I just make them all myself, but there are commercial laser diode drivers that you can buy that are pretty simple, just constant current, so, you know, for laser diodes, you know, of course. But yeah, I just make them now, so, and usually they use I usually use pretty ridiculous circuits for it, but like one of them, I ripped apart a microwave oven, like the modern inverter ones, and used the transformer as an inductor and boost circuit, and used that to drive my laser. So it had a microwave, you know, transformer core in it. Yeah.
Right. Let me ask you, how does whether the atmosphere affect the discharge?
Oh, so like,
If you have a high
yeah, so,
level,
yeah, so like how does that atmosphere, so like for the batteries, for the like the low voltage, high current, it's really just the temperature of the batteries that makes a difference. But for like, when I'm doing high voltage experiments, making electrical arcs, I think you can strike a longer gap when it's like cold and dry. I think humidity raises that, like the field you need to break down dielectric, you know, strength. You know, the humidity plays a role. And you know, get longer sparks when it's dry out.
So on that line, say if you can control your atmosphere,
Yeah.
like you have a dry nitrogen versus have oxygen moisture, how would that impact the
Yes.
discharge and current?
Yeah. So like yeah. In fact, because now I have this whole setup for, you know, loading gases into like vials and stuff, so I can excite them with like Tesla coils. And although I still don't have a nitrogen tank, weirdly enough, but yeah, nitrogen, you know, it's not as easy as something like, you know, argon or xenon, because you have to rip apart that bond first before you know, strip off the electrons off the atoms. But so yeah, I mean, there's big differences. You know, the noble gases ionize way easier than the, you know, diatomic molecules. Yeah.
How much do you think it'll cost before you get the estimated like results that you want of it crushing the pipe?
Well, I might be able to crush the pipe with what I have, and that would be ideal, you know. But if I wanted to use FCRs to switch the bank, it probably cost about $10,000 to build a big solid-state switch for it. If I wanted to be like really robust and done right, but I might be able to do it with like, you know, if I get a lucky clean shot with the switch I have now, I might be able to pull it off, especially if one of the other techniques works. Yeah.
So what's your electricity bill?
My electric bill, it depends. You know, it's not that bad. You know, it's not that bad, but it's you know, charging the batteries isn't so bad. You know, but
Might be a little above average.
yeah.
So, what is a typical Drake project budget?
So what's my budget? So it depends. Like this one is really crazy because, you know, a company reached out and wanted me to do this with 400 car batteries. So this is an expensive video, you know, 400 car batteries alone. They're more than $100 a piece, you know, and then I have all that copper on there, you know, so it's like, it depends on the video. Like some videos I do for as cheap as like $1,000, and then for something like this, you know, it's very expensive. But yeah, it's you know, it varies a lot, you know, but it helps that this is like a hired project. Yeah.
So how do you manage like the spray of the,
Oh, it goes everywhere.
but it lands on all the batteries?
Oh yeah, so the nice thing is, yeah, so do I have to worry about the batteries? I mean, at some point, yeah, it becomes an issue, but for like, you know, it has plastic casing that's pretty, you know, insulating. So yeah, they're covered in little melted craters. I did light a battery on fire recently though, so I had to go out there and like stomp it out, you know. But usually I don't like the batteries on fire.
And like with rain?
Oh, rain's no issue. I mean, your battery in your car gets water on it because there's only like across the terminals it's only 12.6 volts. So even if you throw that underwater, it's barely going to conduct, you know. So I have to keep them charged they do discharge on their own, but that's just from like the chemistry that's happening inside the battery. But I keep them charged, even in the snow, you know. In fact, I should point out, my original 100 car batteries still test almost new just because I've always kept them charged. So they handled it, they're totally fine with the short circuiting as long as I keep them charged afterwards. Yeah.
Would you go up to 500?
Oh yeah, I do 1,000 batteries, yeah, I do 1,000. Yeah.
Just get what's
But yeah, hey.
Oh,
So,
hi.
made not magnetic poles or to a fusion?
So I've wondered that, you know, I've wondered that because like, you know, even though they're like cotton, they're like, you know, long pulse currents, the magnitude of the currents is still there. So I wonder that, you know, if I can detect like, you know, if I put like deuterium in there or something, if I can detect like neutron flux. Because I mean, the currents are enormous. It might be possible. Yeah, you might be able to get fusion events from those forces. So the feel of it, like if you just treat it as a, you know, as a cable, it's on the order of a Tesla, at least for like a fat cable, you know. So if you get it through a finer filament, it's just going to keep getting bigger around that. So I don't know about the internal fields with like a, you know, but it should be,
Yeah, 1 centimeter close, it will be about a Tesla.
Okay.
Mu naught I over 2 pi r, 10 raised to minus 7, and you have a current of 10 raised to 5. 1 centimeter, so it's exactly 1 Tesla.
Get it to 30.
Okay, and I do want to do a Zeeman effect experiments because I have these low pressure sodium lamps, and so they make this like really, really narrow spectrum light, and so there's a trick where you light like a salted flame and you put it near the lamp and the flame looks black because it absorbs the light from the lamp. Well, I'd like to put one of them in like a magnetic field from this so you can turn off the black part and turn it back on just with the field. So that is an experiment I want to try with these. So yeah.
Yes.
So earlier you had mentioned a carbon arc lamp.
Yeah.
Would you power it with this?
Yes. So one of the experiments I'm going to do that is going to make one of the most powerful carbon arc lamps ever operated. So yeah, I have these like giant, I mean they're like this fat, these huge, you know, graphite electrodes. And carbon arc lamps were like a really old form of lighting, going back to the 1800s. And so I'm going to try putting, you know, megawatts through one, and yeah, it should be fun.
From here? Yes, Lance.
How often do you have to check in on your contacts for your batteries with all the hot rain?
Yeah, so like I usually I don't go and check the contacts very often just because like anytime I undo it I have to clean it every time. But usually they stay very clean. Like when I pulled the contacts off the battery bank that sat outside for 2 years, they were very clean under all those. So it was as long as I really torque them on tight, then they stayed like they look like brand new shiny copper.
Corner?
How do you learn most of the stuff you need to know for your videos? And were you in any of the design teams at SIU for
Any of the what teams?
design teams?
Oh, I wasn't on any design teams here. You know, I worked at the Goodson lab, you know, but I mean, you know, I did my degree in chemistry here. I guess, you know, for like the electronic stuff, you know, and of course I took his electromagnetism, you know, class, and that was a really good class for me because like before that I followed schematics, but I really didn't know, you know, much about electromagnetism, so it was really helpful to like bridge that gap. But I mean, a lot of this stuff, it's hard to just like, it's like such a specific thing. It's hard to just like, you can't just take like a class on like shorting out, you know, 400 car batteries, you know. So it's just like a lot of it I just have to learn from, you know, reading obscure sources and basics of like, you know, electromagnetism. You know, just, you know, a lot of online reading, I guess. Yeah. Mm-hmm.
What's your laser pointer?
Oh, my laser. Oh, it's funny. So this laser pointer I built, I think 12 years ago. I used an engineering sample of this like nice, you know, sky blue laser diode, and you still can't get these laser diodes. So like even after all these years, this is like a very rare color to encounter. So yeah.
Very nice.
Beautiful. Yeah.
What is the company's like stake in this? Like, are they hoping to
So they see it.
research out of it?
Well, so you know, you asked what why the company did this, and it's just like a crazy marketing stunt. Like they say that they want to be like the Red Bull of science. So you know, I don't have any like restrictions on what I can do. They just want to see what I do with all these batteries. You know, so you know, I try to get the most currents and you know, blow things up and get some magnetic stuff.
So you said they supplied all the car batteries, but there's also hundreds of pounds of copper.
Oh yeah, they bought all of that too.
So they bought
Yes,
all of that.
yes, yes, and paid me for my time. Yes.
So they're fronting all the expenses and paying you.
Yes, yes. Yes, it's pretty bizarre.
That's like,
Do you use any high-power semiconductors for your experiments?
Yeah, so high power semiconductors. So it's funny because like a lot of the power switching I do, I use vacuum tubes just because they're robust and they work at high frequency. I did build a really high powered solid state coil using the silicon carbide MOSFETs, but I've never posted about it. But yeah, most of what I do is archaic. I love vacuum tubes just because you can run them with like a high supply voltage because you know silicon is pretty limited on voltage. You know, not to say there's not ways to get around that, but like I have this RF oscillator I built that uses a vacuum tube. It runs like 13 megahertz, but it's like such a chaotic device that like there's no way to do what I want to do with silicon. It has to be a vacuum tube because it would get silicon would get killed by over voltages. But I still I dabble in it, I guess, and I do have future projects where I would like to use more semiconductors. Yeah.
More questions?
I feel like the bucket of mercury could work.
Yeah. So the bucket of mercury, it's a slow turn on. Mercury is also very resistive for a metal. It's very resistive, so it would limit the current unless you use a small gap, but it also has such high surface tension, it'd be hard to put it in there. So the other issue is like the first part that would touch would be mercury vapor. So like you'd have to really dump it in, you might need a pump to like splash it in.
You have the contact already, like one contact in the mercury.
Oh yeah, that could work too. And of course you'd explode off some
And you
of
do it
that.
on a windy day.
Oh yeah, the vents and the mercury vapor. Mercury is expensive these days. Like I remember I bought some as a kid for $10 a pound, and now it's like $200 a pound if you try buying it. So invest in mercury, not gold.
I was thinking like about like some sort of, you're having these weird oscillations with your switch, but some sort of liquid switch or gaseous switch, right? Where you can do it like pneumatically, where you just let gas in.
So like gas conductor or like pneumatic actuation? Because like
gas conductor.
So there are devices like ignitrons that work on that, and thyrotrons too, I guess. But they all have a big if you're conducting through a gas, you got to ionize it first, and those have a strike voltage. And even regarding the striking voltage, the on-state voltage is still pretty high, and I only have 65 volts to start with. So like you get a big voltage drop across gaseous or plasma conductors. So that's but even something like a mercury ignitron, I think it might be possible using mercury vapor as the conductor, but then again, those devices, they can handle huge peak currents, but not like sustained currents. They make a lot of heat. Because if I have 65 volts and you drop 10 of it, 10 of it at 150 kiloamps, it's 1.5 megawatts you're going to dump through your switching device. And most things don't like that.
Keeping time in mind, let's close it up. Let's thank Drake again.